Welcome to ECE 165. This is lecture 5. In this lecture, we're going to talk about how do we analyze in a more general and perhaps easier sense the delay that we're going to experience in digital CMOS logic gates. Now, the specific technique that we're going to learn about in this lecture is called Elmore Delay analysis. Once we've learned that, then we will get in a little bit into a technique called logical effort, which we will then expand upon more in the following lecture. So what we're going to do now is introduce a delay analysis technique that we refer to as Elmore delay. Okay. Now what we say is that most digital circuits can be modeled as an RC tree, or tree of resistors and capacitors. Okay, the Elmore delay technique can approximate this delay. And in fact, it does a pretty good job at approximating this delay. Okay, and hopefully we'll see that with an example. So what we'll say is the delay, the propagation delay, is equal to the sum over all I of R n minus I times Ci. Okay. Another way to state this is sum of I equals 1 to n of Ci times the sum of j is equal to 1 to I of Rj. Okay, and that is the Elmore formula. Clear? Okay, of course, this formula perhaps doesn't make a lot of sense until we dive a little bit more deeply into this. So what we say is Rn sub n minus I. We call this the shared, and let me be more clear in my writing here, the shared resistance to the output on a path to capacitance Ci. Okay, so that still might not clear everything up. So let's go ahead and label what Ci is. Ci is each capacitor in the RC network. So we essentially consider each node that the capacitance, each node that has capacitance in our network, and we multiply by the sum of the individual resistors on this shared path. Okay, so essentially we're trying to assess the total resistance that each capacitor sees along its way to the output, and we multiply that total resistance by the capacitance at that node, and we sum up over all of the capacitors on all of the nodes, and that's how we get the eventual delay through our Elmore network. Okay, so this is perhaps still a little bit of an abstract formula, so it's best understood by going through an example, and hopefully by going through this example, things will become clear. So in this example, we want to design a 3-input NAND gate, or a NAND 3 gate, with equal pull up network and pull down network drive strength. So that's step 1 of the problem. Once we do that, we want to estimate the propagation delay of the falling edge. Okay, so first of all, let's go ahead and build our 3-input NAND gate. Now you could do the technique that we learned in one of the earlier lectures where we kind of build up our device through Boolean algebra and useful constructs. In this case, a 3-input NAND gate is fairly straightforward. Essentially what we have are 3 PMOS devices that are going to operate in parallel and 3 NMOS devices that are going to operate in series. Okay, so these are PMOS devices up here and our NMOS devices on the bottom. So the first step here is, how do we want to size this circuit? And I should perhaps label the output node. This is Vout here. Okay, so we want to first size this circuit so that it has equal pull up and pull down strength. Okay, so in fact, we actually, usually when we do this, we want to design our circuit to have the same effective speed or drive strength capabilities, more precisely, as a unit-sized NMOS, unit-sized inverter. So what that means is the NMOS transistors, in order to have the same effective on resistance as a unit-size inverter, we need to upsize these transistors by a factor of 3 so that each resistor is R over 3, and when we sum them all together, we get a total resistance of R. Now, in the pull-up network, we usually want to consider the worst case resistance. Okay, so typically in digital CMOS circuits, we want to make sure that our circuits operate under the worst possible scenario. And in this case, the worst possible scenario is when only one of these PMOS transistors turns on. Of course, if all of the PMOS transistors turn on, all of the resistors combine in parallel, and we get an effectively lower resistance, which is desirable and therefore not the worst case. So in the worst case, only one of these PMOS transistors will turn on, and if we wanted to have the same effective on resistance as a unit size inverter, they need to have sizes of 2. So if only one of these guys turn on, then its effective resistance will be 2R over K. In this case, K is equal to 2, so that's 2R over 2, or just R. That's the same strength as our minimum sized inverter. Okay. So what we can do now is we can go ahead and represent this using our useful constructs and draw an effective circuit diagram. Now, this is going to get a little bit complicated, but let's go ahead and do our best here. Okay, so we have our PMOS transistors. They have some capacitance, a switch, and some extra capacitance here. So that's one PMOS transistor. Then we'll just effectively repeat this 2 more times. Okay, there's the second one. Here's the third one, switch, capacitance. There we go. Okay, so that is the
pull-up network. This connects to Vout. Then we want to look at the pull-down network. And in this case, we have 3 NMOS transistors. I'm just going to draw these capacitors on opposite sides just for a little bit of clarity here. Okay, we're just able to fit this in here. All right, so let's go ahead and label most of these devices. So this is R, this is 2C, 2C, R, 2C, 2C, R, 2C, and 2C. Now, each of these NMOS transistors is R over 3 and 3C on the source and drain terminals of all of these devices. R over 3, R over 3, and 3C and 3C. Okay, perfect. All right, so let me just make a few notes here. So again, this is our worst case pull-up resistance. When only one of these transistors turns on, that's equal to R, so that's good. That's the same as a unit size NMOS. And all of these, when added together, the total pull down network resistance is equal to R. Again, also the same as a unit size inverter, so I think we've been doing our job well here. Okay, so we are interested in analyzing the pull down
propagation delay, or the propagation delay of the falling edge, which means we'll assume that the PMOS transistors, one or all of them, were all connected initially to VDD. And then at some instance in time, all of their switches open and all of the NMOS transistor switches close, therefore connecting the output to ground. And so what this means is that all of these capacitors at all of these internal nodes have to discharge from VDD to ground. Now you might say, well, we actually need to know the status of what these switches were to know what the pre-charged voltages of these internal nodes were equal to in order to analyze this circuit. And you're absolutely correct. We're going to, for the moment, ignore that, and let's just assume all of these capacitors were originally pre-charged to VDD, and we have to discharge all of them. All right. Now, there's a few other simplifications we can make. We can, of course, get rid of that capacitor. These PMOS capacitors, because they're connected to VDD on either side, they don't participate in charging or discharging in this particular circuit. All right, so this is still a little bit complicated. So what I'm going to do is I'm going to combine all of the effective parallel capacitors that I can and make a slightly more simplified circuit for us to analyze. All right, so that's simplified. Simplified circuit is going to look something like this. We have 6C of capacitance from our PMOS transistors at the top of our circuit there. Then we have 3C of capacitance from that first NMOS transistor, goes through R/3. We have, in this case, 6C of capacitance, because we're combining the capacitance of two transistors, the source and the drain of two transistors. We have 6C here, and then that goes through a final R/3 circuit. Okay, so the first thing we might say is, well, let's just sum up all the R's and C's and say, you know, is the propagation delay equal to all of those R's? So that's R/3 times 3. Times, if we go ahead and add up all those capacitors, we find we have 21 C of capacitance. So is the delay equal to 21 RC? And the answer is no. Okay. The answer is no, because that's just, you know, too simple, right? We just summed up all of the R's and C's and just kind of said it's one RC delay. But in reality, it's a little bit more complicated than that. It's a tree-like network, which means we need to use the Elmore model, the Elmore Delay model. Okay. Now, if we do that, we go ahead and we look at the capacitance at every node and write down what's going on there. So let's take a look at node 1 first. At this node, we have 6C of capacitance, and it goes through R/3 amount of resistance. So we'll label that node 1. Okay. Node 2 here, we have another 6C of capacitance, and in this case, it goes through 2 times R/3 resistors. Okay, so we'll label that as node 2. And then node 3 at the output, it has 9C, and let's just write this for your notes, 3C plus 6C of capacitance, and it goes through 3 times R/3 amount of resistance. So that is node 3. Okay, so if we go ahead and sum this up properly, we get a delay of 15 RC. Okay, and that is much more accurate than just blindly summing all of the R's and C's together. Okay, so this is the beauty of the Elmore model, is it's fairly simple once you kind of understand what those summation equations mean. And when you go ahead and do that, it's you know, it's fairly easy to execute that formula, and we get a much more accurate result than just simply summing up all the R's and C's and assuming it's just one RC delay. Now, one specific point that we kind of have overlooked in the Elmore delay model is that we always said that the delay model had to use the shared resistance on the output to path on the output path to capacitance CI. So let's take a look at an example where that may not be so obvious. So let's take a look at a more complex pull-down network. Okay. So what we want to do is calculate the delay the pull down delay to V out. Okay, and in this network, we're going to, I'm not going to draw a transistor model, but you can imagine a circuit that might look like this. So we have some resistance here. We're going to call this R11. This is capacitor C. This path is going to split off into a couple different paths here. This is capacitance C. This is R2. And then we're going to have another path going this way. It's going to be loaded by capacitance C. This is R12. And this is R13. Another capacitor C here. And we'll call this one V out. Okay. So each of these nodes here, I'm going to label this node 1. This will be labeled node 2, node 3, and label this node 4. Okay. So we are trying to discharge V out. So it has some path of current that's going to follow this way. Okay. So we'll call this path 1. And we have another path that's going this way, and this is path 2. Okay, so if we assume that all of these capacitors were originally pre-charged to VDD, then what we have to assume is that all of them are going to discharge to ground. Okay, now if we go ahead and execute the Elmore delay formula, we get something that looks like this. So at node 1, we have C of capacitance, and that's going to multiply by R11. That's the amount of resistance on that shared path. Okay, so we'll call this node 1. Now let's go ahead and look at node 2. Here we have C of capacitance, and now we're going to have R11 plus R12 as the resistance along that shared path. Okay, so far so good. At the output, we have C of capacitance and R11 plus R12 plus R13. Okay, so far no surprises here. Now here's where it gets tricky. So we say that node 4 has C of capacitance, and from node 4 to ground it has R11 plus R2. Okay, however, according to the Elmore delay model, we don't have to include R2 in this Elmore calculation, okay? And the reason is that is not on the shared path to the output, okay? So we don't really care what happens at node 4. We only care of the propagation delay to get V out to discharge to VDD over 2, okay? So we don't really care what happens at node 4, all right? Now let's just go ahead and make a note here for your notes. This is the shared path resistance to the output. Okay. So this node 4, certainly it doesn't use R12 or R13. I think that's clear. But the question is, why don't we include R2? And the reason is, let's consider what would happen if C was at node 4 was an enormous capacitor, okay, and all the other capacitors were very small. Well, what would end up happening is that V out would discharge fairly quickly because all of these other capacitors are fairly small, whereas node 4 would probably take quite a bit longer to discharge itself. Okay, now we have to include node 4 in our Elmore delay calculation because there is current that is discharging through node 4 to ground, and that means there's a resistive drop across R2, which means that it's going to impact how node 1 ends up looking during this discharge phase here. Okay, however, R2, what happens if R2 is for example, very large? That delay that discharge could take quite a long time. Alternatively, you could have a thought experiment that says, what happens if R2 is very small? This could affect how the circuit behaves. Okay, and so effectively, what we're trying to say here is that we only care about what's happening at the output node. So therefore, we only care about the shared path resistance to that output node. What current is flowing through the path from the output to ground? And that current will certainly include what's happening at node 4. However, the resistance of R2 is not as relevant. Of course, it's slightly relevant, but according to the Elmore delay model, it's not as relevant as the other nodes. So for the purposes of Elmore delay model, we will neglect that node. So now I'd like to move on to another topic called logical effort. And by the way, if this shared path resistance thing doesn't make a whole lot of sense to you, I do recommend reading the textbook about it. They go through this sort of example here. Okay. So those of you following at home, logical effort is described in the Weston Harris book in sections 4.4 and 4.5. Okay, so what does logical effort mean? It sounds kind of like a strange term, but let's go ahead and build up some definitions, and then we'll see what logical effort ends up being all about. Okay, so let's recall the RC delay of an inverter. Okay, so we said, we have some inverter. Let's, in this case, analyze a loaded inverter. This is INV1, INV2, and let's make these of size 3 each. Okay, so what we said is we could go ahead and represent this circuit. Let's say in the pull-up delay case, we have some sort of R on from inverter 1. It's connected to the output. The output has CINV1, and let's just assume that NMOS switch is open. That there's some parasitic capacitance at the drain of inverter 1, and there's some gate capacitance at the gate of inverter 2, and this is some wire that's connecting them. Okay, so what we say is that the propagation delay is equal to R, the R on of, in this case, our PMOS transistor, times CINV1 plus CINV2, okay, which of course is equal to R times CINV1 plus R times CINV2. Okay, so we're doing some very basic algebra here, but I'm just separating this to say that this is the intrinsic delay of the deriving inverter. And this term here is the extrinsic delay, which depends on the load. Okay, so what we can do is we can rewrite our propagation delay as follows. Okay, we're going to say that D is equal to P plus F. Okay, so we're getting into a little bit of an alphabet soup here, but and it will in fact get much worse in terms of the alphabet soup. But hopefully, once we kind of get through all this alphabet soup, we'll see that this is a very powerful technique. Okay, so we say that the delay through this circuit is equal to P plus F. We'll describe what P and F are momentarily. But first, let's say the propagation through our delay through our circuit will just be equal to this D term times tau INV. And we said define tau INV as being equal to 3RC according to the class sizing convention. Okay, so what does P mean? P is the parasitic delay of our circuit, and this is intrinsic to the gate even when not loaded. Okay, so let's say this is intrinsic to gate even when not loaded. Okay, and then we'll say that F, let's just make an arrow coming out over here. F is the, we're going to call this the effort delay that depends on the load capacitance. Okay, so all what we're doing here is we're saying for any logic gate, we can normalize our delay to be the sum of the parasitic delay, or P, which is intrinsic to the gate. Even if there's no load, it still has some delay, has some parasitic capacitance at the output terminals, etc. And an effort delay, which is the effort the gate needs to exert in order to drive whatever happens to be loading it. Okay. So again, you might be like, well, why are we doing this? This is just, doing the same thing, but making it unnecessarily complicated. And, without understanding further, you're right. However, the further we go, we'll see that this ends up being a very powerful tool to actually optimize delay through digital CMOS circuits. That's really the whole point of doing logical effort. Okay, so we normalized our delay to equal to P plus F. Let's write down some more notes. Since we normalize D to a unit sized inverter, let's define P and F, our parasitic and effort delay, with respect to a unit size inverter, in this case abbreviated as INV1, as well. Okay, so specifically, let's say the definition of P is equal to the load capacitance of our circuit divided by the load capacitance of a unit-sized inverter. Okay. So that'll be the definition we're going to use for P if we're going to analyze a non-unit size inverter, for example. The definition for F is going to be equal to G times H. Okay, so yes, I hear you, more alphabet soup. However, bear with me. We'll get through this, and at the end it will make hopefully a lot of sense and will become a very powerful optimization tool. Okay, so we're going to call G is called the logical effort of the circuit. Okay, it's the logical effort of the driving gate and is a function of gate complexity. All right. Now, specifically, according to this definition, we're going to say G is equal to the input capacitance of the gate that we're analyzing to the input capacitance of a unit size, or of an inverter sized to have the same drive strength capabilities. Okay. Now, H is what we call the electrical effort, which is a function of the ratio of external, or in other words, load, capacitance to the input capacitance of the driving gate. Okay, so the definition here is then C external divided by C internal. Okay, so we're getting a little bit into the weeds of some alphabet soup. Let me be a little bit more specific with the definitions, at least in words. So what I want to say is more specifically, G is, quote, the ratio of the input capacitance of the driving gate to the input capacitance of an inverter that can drive the same current. Okay, so what does that mean? That means effectively it's the input capacitance of the driving gate compared to an inverter that effectively has the same R on, or in other words, can drive the same amount of current. Okay. Similarly, P is, quote, the ratio of output diffusion capacitance of the gate in question to the output diffusion capacitance of an inverter. So it's the ratio of the output diffusion capacitance of the gate in question to the output diffusion capacitance of an inverter with the same current capabilities, or the same drive strength capability. So it's kind of the same condition as for G, but in this case we're looking at the output diffusion capacitance of the gate rather than the input capacitance. Okay, so again, all of these definitions may seem a little strange. Sometimes it's best to go through an example. And in this case, let's take a look at a NAND gate. Okay, specifically a 2-input NAND gate. So in this case, we have 2 inputs here connecting to 2 NMOS transistors there. And let me go ahead and just kind of be more specific and say this is input A, this is B, input B is also connected over here. Okay, so first of all, let's size this transistor, or this gate rather, to have the same current carrying capabilities as a unit size NMOS in the worst case. In the worst case, that means our PMOS transistors will be of size 2, because in the worst case, only one of them will be on at a time, and they will have the same current carrying capability as an inverter. And the NMOS transistors have to be upsized by a factor of 2 in order to support the increased resistance of the series combination of those 2 transistors. Okay, so we can go ahead and compare this to an INV with the same current capabilities. Okay, so we can draw an inverter, and the trick is how to size it correctly to have the same current capabilities. Well, you know, we kind of actually already went through this exercise when we designed the NAND gate, but let's just go ahead and do this again. So again, in the worst case for the NAND gate, for the pull-up network, the worst case is when only one of those devices is on at the same time, and therefore, if we want an inverter with the same current carrying capabilities, we just need to size that NMOS to be of size 2. Or sorry, the PMOS to be of size 2. Now, the NMOS pull down network, in the worst case, both of those guys are on when the circuit is pulling down. Both of them have a resistance of 2R over 2, or sorry, R over 2. And when we add them up together, we have a total resistance of R. And in order to get that for an NMOS transistor, we just need to size that NMOS transistor to be of size 1. Okay, so we can say here that for our gate, we say that Cin is equal to 4C because we have, you know, connected to input A or B, we see 2C of capacitance each at the PMOS and the NMOS transistor, so our total input capacitance is 4C. We only need to consider one input. So therefore, our logical effort, our G, for our NAND 2 gate is going to be Cin NAND 2 divided by Cin INV with the same current carrying capability. That is equal to 4C over 3C or 4 over 3. Okay. We can do the same thing for the parasitic delay. NAND 2, that's equal to CL NAND 2 divided by CL INV. And that's equal to, in this case, the total output capacitance of our NAND gate is 6C because we have two PMOS transistors and one NMOS transistor connected to the output, divided by 3C for the inverter, so that's a factor of 2. We can also try to compute the electrical effort of this gate, but this depends on the load. So we can't do this in isolation. We need to know what it's driving. So in order to compute what H would be, we need to know what it's driving. So let's just go ahead and take a look at an example. Let's compute the delay of a loaded inverter using logical effort. Now we know how to do this problem using Elmore Delay. But for fun, let's use logical effort and see if we get the same answer. Okay, so, and of course, this is a bit of a toy example, but hopefully it will make everything about logical effort clear, which will help us moving forward. So let's say that these inverters are each of size 3C. So this inverter has a 3C output capacitance. This inverter has a 3C input capacitance, and let's just go ahead and separate the circuit into different parts here. So this is the input of the circuit. We have 3C of input capacitance looking in this way. This is the internal part of the circuit, and we'll call this the external part of the circuit. Okay. All right, so let's go ahead and write down our logical effort expressions for our inverters. The logical effort of a inverter is, well, by definition, you're comparing it to an inverter, so therefore it's going to be equal to 1. The electrical effort, as you recall, is the ratio of the external capacitance to the internal capacitance. So in this case, the external capacitance of our external inverter, there is 3C. The internal capacitance is 3C, so this is also equal to 1. And the parasitic effort is equal to, well, 3C over 3C is also equal to 1. Okay, so this is kind of a trivial example, but let's go ahead and make sure we get the right answer. So we say that delay through our circuit is equal to P plus F, the parasitic delay plus the effort delay. P is the same. The effort delay is just equal to G times H. So we get 1 plus 1 times 1 is equal to 2. So therefore the delay, the propagation delay through this circuit is equal to D times tau INV, which is equal to 2 times 3 RC, and that is equal to 6 RC. Now you should recall that this is, yes, equal to what we got through our earlier exercise. Okay, so again, you might be thinking to yourself, why are we doing this? This is just, kind of a more complicated way to get to the same answer. Okay, so bear with me. Logical effort turns out to be a very powerful technique to very quickly be able to analyze the delay through circuits, and also very quickly actually be able to optimize the delay through circuits to have them operate very quickly. Okay, so this has been a quick introduction into logical effort. Please take a look at the notes that I'm going to post online. They have some tables for the logical and parasitic efforts of typical logic gates like NAND gates and NOR gates for a variety of different inputs. Please take a look at those tables. They're of course also in the textbook. They're kind of useful to refer back to, so you don't have to kind of derive the logical effort of basic gates every time you want to analyze a new structure. Okay. Now, in the next class, we're going to learn how to take a look at multi-stage, having NANDs and NORs and inverters all connected together, and very quickly analyze and thereafter optimize the delay through these types of circuits. Now, just before ending this lecture, I just wanted to show you some useful tables that you may want to refer back to as you're doing more complicated multi-stage design. This will become particularly more important as we get into the topics of the next lecture. But these are tables, I believe they are 4.2 and 4.3 from the Weston Harris book. And they show the electrical efforts and parasitic efforts for a variety of common logic gates and for NANDs and NORs and so on for various numbers of inputs, including a general number of inputs n. All of these you should be able to derive with the techniques that you've been computing or that we learned already in this lecture. But sometimes, you have a big complicated logic circuit and you don't want to have to rederive everything, so these tables can be useful as a future reference.